Okay. Huh? Okay. Okay, and I want, what do I want here? I want, no, 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 yeah. Okay, we are on page 73, 73. Hey, huh? Oh, we don't. They were very popular. You didn't get an A? Nobody got sent down? But they were all gone? That sucks. I'm so sorry.
Is that why?
I don't know. No, I think they must have just run out or something. I'm so sorry. They were good pears. I didn't eat one, but everybody said they were pretty good. Page 73. Phones away, page 73. Yes. Doesn't matter. If you wrote bore, you're fine. Even if you got the H and the O backwards, there's many people there. Page 73. So, previously, you have learned how to draw the staircase. So let's draw the staircase, shall we? If you haven't already, or you can tell me where to draw the staircase. Where do I start? Boron, and do I go across or do I go down? I go down. So just do-do, 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 do-do. Why can I not draw properly? There we go. All right. Now, it also says to shade the non-metals. Now, I have to be honest with you. Very often, I just ignore the metalloids. Yes? And so if I say shade the non-metals, and you shade everything over here, that's okay. Oops, not that one. But if you chose to not shade the metalloids, that's also okay. So that would be your non-metals. Yes. We are on page 73. No problemo. Yeah, somebody should be saying wait. Yeah. 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 So I could say boron, silicon, arsenic, tellurium, and then we're not going to worry about astatine or the other ones because they're too far down and it gets all goofy near the bottom of the periodic table, right? So we're not going to worry about it. All right? But these guys are metalloids. So if you chose to not shade them, that would be okay. Now, those are the metalloids that are on the right-hand side of the staircase. Who are the metalloids on the left-hand side of the staircase? Yes, germanium. SB is antimony, which is just such a weird one. And then once again, we get down into polonium, and I don't know, if you shade it, that's fine, but if you don't, that's fine, okay? What about aluminum? It's a metal. It is shiny. It is hard, okay? It will conduct electricity. It is a metal. It's not a metalloid. All right. You should still be saying, but wait, Ms. Spence, I forgot hydrogen, and you're not supposed to. Don't forget the hydrogen. Okay, so if you forgot the hydrogen, make sure that you also have hydrogen, which is also a non-metal. Now, why am I going over this again and again and again? Right, we did some of it last day, we did some of it the day before. Why are we going over this? Because on Monday, and I'll show you on Teams, if Teams will wake up, we have an upcoming quiz or test, but this one's a quiz. And sadly, I can't really make it bigger, but you can feel free to go and read it. There's a quiz on the periodic table. You need to be able to label all the groups that we've talked about. The alkali metals, alkaline earth, transition metals, halogens, noble gases. If you're doing enriched, you should be able to label the lanthanides and actinides. You should know which groups are the main group elements. You should know that the columns are called groups and the rows, which are horizontal, are called periods. You should know that the elements that touch the staircase are the metalloids, all except aluminum, which is a metal. And then we're going to learn today about number 6, which is there is one property you are responsible for knowing about metalloids. And that is that they are semiconductors. And the reason I'm making that one mandatory for you to know is that if it weren't for the semiconductive property of metalloids, especially silicon, but also germanium and a few others, but especially silicon. Have you heard of Silicon Valley? Yeah? Silicon Valley is where the tech revolution sort of, was at its most like crazy. Okay, back in the 2000s, it's still a technology hub. Okay, and it's all because of silicon. Silicon is responsible for all the microchips in your phones, in your computers, in your cars, in anything that has any, in your smart TV, in anything that uses that kind of thing. It's all because of silicon. Okay, and that's why you need to know that metalloids are semiconductors. That doesn't mean you're going to understand much about it right now. What does it mean, do you think, that they are semiconductors? Yes. They conduct electricity, but not super well, okay? And that is the special thing that makes them really good at being in microchips, okay? And if you're interested in that, you can go and study that in university, okay? We touch on it a very, very small amount in Chemistry 11 Enriched, but beyond that, not very much. You should know the two elements that are liquids at room temperature, which we are going to go over in a moment. See if you can tell your partner if you know any elements that are liquids at room temperature. And if you don't know, don't worry, we'll tell you soon. Okay, so you need to know those two. You also need to be able to list the 7 properties of metals and 7 properties of nonmetals. If you're doing the non-enriched version, the first column will be given to you. And if you're doing the enriched version, the first column will be blank and you will fill it in yourself. You also need to be able to define malleable, ductile, and brittle. Now, hopefully you read about this last night, but we're going to go over it again today to make sure you didn't miss anything, okay? We won't spend too long because I know you've already taken a look at it. What do metals, what is their appearance? They are shiny, yes? Non-metals are not shiny, and we say that that is dull. Okay, so we have shiny and we have dull. What state of matter are most metals? Solid. And this is where you get into your one liquid. The one liquid metal at room temperature is mercury. So you need to know this exception. You need to know that these guys are solids, and you need to know that mercury is a liquid. You need to know this exception. So literally on your quiz, there's going to be a periodic table with some boxes for you to label, okay? There's going to be another periodic table for you to draw the staircase on and shade some things, okay? And then there is going to be this table for you to fill in, okay? And then a couple other questions. I will literally give you a practice quiz to do over the weekend, okay? And you'll be practicing tonight as well. All right, solid, and now nonmetals. Yes? Do you want them? No, okay. I'll try to make sure they're not there, but if they are there, you can just ignore them. You can just be like, your pencil can trail off into nothingness. Yes? Okay. So nonmetals, people would like to say, metals are solid, therefore nonmetals are gas. That's not true because the stuff, do you guys know what your pencil lead is made of? It's actually made of carbon. It shouldn't be called a pencil lead. It should be called a pencil carbon, okay? And if you look at your lead, it's not really shiny in the same way that a metal is shiny. It might have a gloss to it, but it's not shiny in the same way as a metal. It is dull. Yes, yeah. So some of your nonmetals, like carbon, are solids. Have you guys ever seen the sulfur piles down in Port Moody? A few of you have. Let's go and look and see if we can find the sulfur piles in Port Moody. Port Moody sulfur piles. I'm going to regret this, aren't I? The little circle's going to go around and around and around and around. Images. Look at those. Okay, so literally, if you go out to Port Moody, if you get the right angle, you can actually see these huge piles of sulfur. Yeah, right? And so it is a solid, and it is yellow. Sulfur is yellow, just like your periodic table. It's very much the periodic table color, yes? Yeah. Okay, so, yes. Why are they there? That's a good question. Let's see. Did it tell us anything about them? I mean, sulfur is useful for a lot of things, including, what do you call them? Fertilizers and production of like other acids and stuff. Let's see. Wastewater and rainwater treated and keep dust down from the. Does it say? Okay, you know what? I'm going to look it up and then I'll get back to you on that because I feel like we'll just, watching me Google things and read them is not very much fun for you. So let's skip that part. I'll do that part and come back to you next day. Okay, back to here. Okay, so about half of the nonmetals are solids, like the carbon in your pencil, which is called graphite, and like the sulfur. And then, as you can tell from the name noble gases, about half of them are gases. There are other gases in addition to the noble gases. Chlorine is a gas, fluorine is a gas, okay? Oxygen is a gas, nitrogen is a gas. You probably knew about oxygen, you might have known about nitrogen. So about half are gases, half are solids. Okay, so you need to know that half are gases. Did I get the right color? There we go. Let's make gases green. G for green, G for gas. Half are gases, half are solids, and then we have our other liquid element at room temperature. Who is it? It is bromine. Okay, bromine is a liquid. And so you need to also know this exception. There will literally be a question that says, list the two liquid elements at room temperature. Like, there's not going to be any surprises on this quiz. Like, it's literally like that is a question. Know this exception. All right, good, good, good. Now let's imagine, do you guys know what density is? So if I had something in my hands that was very dense, what would happen? Ooh, it'd be heavy, right? I'd be like, oh, okay. Like a gold bar. Apparently when my husband was a little kid, his family went to Fort Knox in the United States, which is where they keep their gold and whatever. And they told the little kids that they could take out as much gold as they could carry. Because, you know, little kids, little spaghetti arms, right? Like, and they would try and pick it up and they couldn't. And the gold bars are really only about, you know, the size of one of these erasers for the chalkboard. They're about that size. Now, this eraser for the chalkboard, this is light. It is very low density. So this little eraser would be low density. And guess what? It's made of carbon and hydrogen and a bunch of nonmetals. So it is not very dense. It feels light for its size. It's also because there's a bunch of air in there, but I'm cheating and just telling you it's because they're nonmetals. But metals tend to be more dense. Aluminum is a fairly light metal for its size. And you'll notice it's very close to the dividing line between metals and nonmetals, so it is less dense than some of the other metals. So the density of metals is high. The density of nonmetals is low. You are responsible for knowing the word malleable. So how are you going to spell that? You're going to spell the word mall, like going to the mall, okay? And then you're going to put E, and then able. So mall-e-able, mall-e-able, mall-e-able. Except for we pronounce it malleable. And let's imagine that you are a blacksmith, okay? It's back, it's the Middle Ages, okay? And you've got this horseshoe, all right, on your anvil, and you take your hammer and you hit that horseshoe. Does it break? Hopefully not, hopefully not. It shouldn't, not very much anyway, not very often, because metals tend to be malleable, which means if you hit them, they will deform or they will flatten out, okay? So if you think about cookie dough, if you have some cookie dough and you smush it with your hand, did it break or did it deform? It deformed. Cookie dough is malleable. It is way more malleable than metals, because metals you need a lot of force, right? But, all right. So malleable means they will deform when hammered rather than breaking. You need to know both. You need to be able to write both on the quiz. The word and the definition. Same thing for brittle. You need to write the word brittle. That stopped working, that's good. You need to know the word brittle, and you need to know that unlike the cookie dough, after you have baked the cookie, if you hit it with a hammer, what happens? It will break because the cookie dough is malleable, but the cookie is brittle. Okay? And there's literally a substance called peanut brittle. Has anyone ever had it? It's like peanuts in kind of a really brittle caramel. I didn't like it very much. It's kind of like, it's sharp and it like will cut the inside of your mouth. It was kind of gross. But anyway, I'm like, why would I want a piece of candy that like chops up the inside of my mouth? But anyway, so they will break or shatter when they're hammered. Okay? And again, you need to write both. Yeah, in the chart when you're doing it. Yeah. Okay? You also need to know the meaning of the word ductile. Now, I have all kinds of ways to help you remember this one. Not all of them make a lot of sense, but hopefully one of them will make it stick in your head. So these are able to be pulled into a wire. They are stretchable. Okay? And once again, you need to be able to give me both. Now, there's a couple ways to remember this. Number one, if you look up in the ceiling there, and if you would like to come up and like just take a look and see what you see, there's a big hole in the ceiling. What do you see up there? You see metal, yes? And it's these pipes. What do we often call those pipes? Yes? They're called ducts. And guess what? Metal is ductile. What are ducts made of? Metal. Okay, so ducts are made of metal and they're ductile. What else might you find up in the ceiling? You might also find wires, right? Wire, being able to be pulled into a wire is ductile. You find both the wires and the ducts in the ceiling. Now, I'm going to tell you another one that might help you remember, but it's very silly. I give full credit to one of my grade 11 students from last year because they have a quiz on the same sort of thing to remind them of their grade 9 stuff when they're first starting out Chem 11. And so on his quiz, he wrote ductile, stretchy, like a duck. I was like, what? But it was really funny. It made me laugh out loud. Like I was at home and I was like just killing myself laughing because I'm like, it's stretchy, like a duck. So if that helps you remember that ductile means stretchable, then hey, more power to you. I always have this like picture in my head of like, you know, the rubber chicken. Have you seen the rubber chickens? And I have this duck that's like one of those rubber chickens, but it stretches, right? So I've got this picture in my head. Anyway. So metals are ductile, yes. Yep. Yep. No, you can just choose one. Okay? Yeah. Now, non-ductile, you don't have to define because it's just the opposite of ductile. So you have to be able to write non-ductile, but you don't have to define it. Okay, so this one here, you need to write both parts. Now, hopefully, your familiarity with, yes, you can just put stretchable. Stretchable's fine, okay? Hopefully, your familiarity with certain substances will help you. So, for example, your pencil lead, which is actually carbon, which is a non-metal, is it ductile or is it brittle? If you hit your pencil lead with a hammer, what will happen to it? It will break because it is brittle. Break, brittle, brr. Okay? Now, how do you know if it's a good conductor of heat. What do you make your pots and pans out of? You make them out of metals, so metals are good conductors of heat. That's how you know it's the metals that are good at that. How do you know that metals are good conductors of electricity? You make your wires out of copper, out of metal, yes? Okay. So hopefully you've done this little bit here. We're going to go on and just mention the metalloids. And just so you know, they used to also be called the semi-metals, but they're not called that anymore. Metalloids is the official name. And I'm just going to run through a bunch of the properties in case you are interested, but you only need to know one property. And you're going to tell your partner, what is that one property you need to know about metalloids? The one property you need to know is semiconductors. Yes. Poor, good. Yep, that's all you need to write. Yep. Okay, so I'm going to put a star here, star here, star here. Okay, that's the one that you need to know. Now, just for your interest's sake, why are they metalloids? Well, because they're shiny like metals. However, they are brittle. They're more brittle than metals, so that's a little bit like nonmetals. They're mostly solid at room temperature, which is like the metals, but also like the nonmetals that are close to the dividing line. Okay, carbon is close to the dividing line, sulfur is close to the dividing line. That's where you find all your solids are kind of over near the dividing line. They're typically solid at room temperature. We just said that one. I'm repeating myself, that's okay. And they tend to form, you don't know this word yet, but they form covalent compounds. That means that they bond with other elements like nonmetals do. Okay, so they behave like nonmetals when they're bonding. Do you need to know that for your quiz? No. Okay, those are just for interest's sake. The one you need to know is that they are semiconductors. Okay, and remember, when we get down to this area of the periodic table here, I'm not really concerned about it. So, you know, if it just kind of peters out there, I'm happy with that. Okay? Don't worry about this section. I don't know why I'm using this voice. My dream job was to be a Muppeteer. You know the Muppets? Like, really? Honestly, I don't know if I'd actually be good at it, but if I could be good at it, that would be my dream. I would love it all day. It's so much fun. Okay. All right, and that's it for that. Your homework for today is going to be number 4, 5, 6, 7, 8, blah, 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 the next 2 pages, but we're not going to do that right now. Right now, we're going to take a little quick look at Schrodinger's model of the atom. Okay, because we've been waiting for this one. We've gone all the way up to Bohr, and now we want to take a closer look at Schrodinger. So we are going to go to page 39. 39. And this is just a quick little look, okay? It's not 39? Oh, let's see, what is it? It is 39. Okay, 39. Schrodinger. What's his model of the atom called? Quantum mechanical model. It's also called the electron cloud model. What you are going to see here may make you uncomfortable. Okay? And the reason I say that is it doesn't fit into our lovely little vision of the world where if I have a pen, it's a pen and it doesn't like dissolve into a wave at some point, okay? We're gonna have things like pens, an electron, which dissolves into a wave, which just becomes a wave if you're not looking at it. But the moment you look at it or do something to it, bam, it's a pen again. Okay, so it's weird. And if you feel uncomfortable with this, just remember that better minds than me or you have also felt uncomfortable with this. Niels Bohr felt uncomfortable with it. Einstein felt uncomfortable with it. So if those people can feel uncomfortable with it, so can we. You are not ever going to have to be able to explain anything about it, okay? But I want you to just get a taste of it because it's just interesting, okay? Yes. Yes. It behaves, yeah. So it's crazy. And there's weird stuff like spooky action at a distance. If you want to watch like videos on that on YouTube or whatever, you can go look that up. It's interesting. But we're just going to get this little taste of it right now. Okay.
Quantum mechanics and the shape of atoms as discovered by Schrödinger.
Hi.
We all know about quantum mechanics.
Yes. 39. And you don't really have to follow along. You can just watch. Yes, of course. Okay, I'm going to make that bigger. Okay. Yeah, until you look at it. Are we ready? Okay. Here we go.
Quantum mechanics and the shape of atoms as discovered by Schrödinger. We all know about quantum mechanics, which is of course the physics theory that describes atoms and elementary particles.
I'm a little bit sad about this because what has he done wrong with his elements? The symbols. What has he done wrong with the symbols? Yeah, he put a capital as the second letter. I'm like, but it's okay because he's a physicist, so that's all right. Physicists they're smarter than me. They can not know some chemistry things, and it can make me feel like really smart, okay? But yeah.
How they move around like slushy little waves, and interestingly, it predicts what they look like, what shape they have. It was invented in the first couple of decades of the 20th century by a lot of people all working together. Amongst them were Planck, Heisenberg, Bohr, Davison, Dubreuil, Einstein, and of course Schrödinger. These guys already knew a lot about atoms from the scientists who came before them. For instance, they knew that there are about 100 different atoms in nature, and that these atoms join in larger structures such as molecules, metal lattices, and salt lattices to make everything we see around us.
Okay, so we got our molecules. We've got, like, this would be a salt. This would be maybe like a metal crystal, okay? And then we just have individual atoms, and then we have molecules like that.
But what they didn't know, what exactly was going on the inside of the atom, what it was made of, what shape it has. So they were doing experiments on that. And pretty soon they found out that atoms themselves are composed of smaller particles. They found the proton and the electron, and they were theorizing the neutron. And with the protons and neutrons, they almost immediately knew what the deal was. They realized that they were clumped in a very tiny core at the center of the atom.
What is that core called? Nucleus.
The core was really small. A typical atom is about 300 picometers across, whereas the core is typically 0.01 picometers.
So the atom is 30,000 times bigger than the nucleus, okay? Approximately. 30,000? Yeah, that's right.
So this leaves this big open space in an atom, and they realized that this open space was going to be the domain of the electron. But what they didn't know was exactly how the electrons are filling this space, if they are spinning around or orbiting or what. So they made an initial sketch. They called it the planetary model of the atom, basically the core at the center and the electrons spinning around in big orbits. It was their first idea of what an atom looks like. It proved to be incorrect, but it was a fine enough starting point. It made some very nice predictions, and it allowed them to start doing experiments, and they did. One man who was looking at his experiments was a Frenchman called Dubois, and he was noticing something very interesting. He found that when electrons were forced to interact with matter, either through some physical process or by hitting a detector, that the electrons presented themselves as particles, as hard little balls of matter.
Okay, so you smack an electron with a photon and it gets bounced off just as though it were a particle. Yes, solid little bit of matter. If an electron comes along and bam, hits a detector, it's behaved like a particle. It causes a little flash to go off.
Kind of what you expect them to do. But when the electrons were allowed to move on their own, either by being shot through a crystal or allowed to wander through a vacuum, they always propagated as if they were waves. It was almost as if when you stopped messing around with the electron, it would suddenly fall apart into some sort of wave function, some sort of probability wave that sloshed around all of space and predicted where the electron was likely next to be found.
Okay, it's a probability field. Yay! Does that make sense to you? Sure.
This was the first time they encountered particle-wave duality in matter, and it spelled disaster for their planetary model. Because this model really assumed that the electron stays a particle during the entire orbit and doesn't fall apart into a wave halfway through. So, they needed a new model, but they realized that this model couldn't come from classical mechanics, because classical mechanics makes the same assumption that particles stay particles. In fact, they would need entire new mechanics, some new theory that included the wave-like nature of particles. And this is when Schrödinger entered the picture. He had looked at the experiments as well, and he found one common theme running through all of them. In his insight, he saw one law of nature, one equation that seemed to hold no matter what you did. He called it the wave equation.
Whoa, that's the wave equation. That was in my first year university chemistry textbook, and it scared the tar out of me. I was like, what? There's like Greek letters all over the place. There's squares. There's like a differential here, which is like some calculus stuff. I don't even know what it all means. We never actually had to use it, but the fact that it was just there was terrifying.
Nowadays, we simply know it as the Schrödinger equation because it was the rock-solid core onto which all of quantum mechanics was built. Schrödinger realized that with this equation he was now in a very interesting position. What he could do is take an atom, any atom, take its properties, stuff like its mass and its charge, all those numbers, put that in that equation, do the math on it, and what he would end up with would be a series of pictures that showed what that atom looks like. He went on and did it for hydrogen, which is the easiest atom, it's just one proton.
He's busy doing the math for the easiest atom. Should we start again? Let's watch him do the math.
On it, and what he would end up with would be a series of pictures that showed what that atom looks like. He went on and did it for hydrogen, which is the easiest atom, it's just one proton, one electron, and that one proved to be crucial into unlocking the shapes of all the other atoms. And when he had worked his way through the math, these are the pictures he found.
So if you're like me, you're like, he did some math, and boom, we got these shapes. I don't understand how we got from here to here, but I just believe that some people who are much smarter than me did some math, and it proved that these were the shapes of the orbitals of hydrogen.
Ladies and gentlemen, the shapes of hydrogen. So this then is how an electron fills the empty space in an atom, not by spinning around, but instead with its blobby-shaped wave function, which we call the orbital. What I've drawn here each time is just the same hydrogen atom with the proton at the center, and the electron has been allowed to go into a different orbital each time by giving it energy, for instance. And if you look at this one, these three blobs together form that one orbital. They house that one single electron.
And if anyone is doing the enriched material, if you have a hydrogen atom, its ground state, the electron will be in this spherical orbital. This black bit is just supposed to be shading to show it's three-dimensional. Okay, it's not a really good drawing, but that's what it's supposed to be. Any of these other ones for hydrogen would be an excited state. Okay, so this is one of the excited states of an electron in hydrogen.
And this one makes a fine example. We can look a bit at its properties. What you can do in an experiment is take a hydrogen atom and prepare it in this orbital by giving it some energy, for instance. And if you leave it undisturbed, then the electron takes this shape. It becomes this wave function, this blobby shape.
So, not a particle, blobby shape. Blobby shape that is like a balloon shape and a donut shape and another balloon shape. Okay? That's what the electron does. Welcome, electron.
And if you then were to take a measurement of the electron, find out where it actually is.
Now you're interacting with it. What happens when you interact with an electron? Turns back into a particle. Here it goes.
What would happen is this wave function suddenly collapses. It condenses into a single point, which we call the electron. If you then were to re-prepare your hydrogen atom in the same orbital, maybe give it some new energy, then you can do a new measurement, and you can find that electron in the same blob, or in any of the other blobs. And if you were to repeat this thousands of times, you would end up with a picture very much like this. Note.
Okay, so you just measure it and measure it and measure it and prepare it and measure it and prepare and measure over and over and over again, and the electron appears here and then 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 here, everywhere. Okay, in those shapes.
Notice that there's a high probability of encountering the electron at the center of the blob.
High probability of finding an electron here, in the center of the blob, or in the center of this donut-shaped blob.
There the probability wave function becomes more dense. But there's something interesting about these pictures, of course, something that is, well, staring us in the face. The fact that these blobs are not connected. There's an area in between where you cannot encounter the electron. So it kind of begs the question, how on earth is the electron traveling from one blob to another? Is it teleporting or what? This was one of the important questions that led to 40 years of heated debate that ended up with Einstein saying very angry things about dyes. But
okay, so Einstein didn't like it. In my head, what I think is like it is a blob and then it condenses to a particle. So it doesn't matter where it condenses to, it's just never, it's not like it's here and then it's there. It's like, it's this blobby shape and then it's here, and then it goes back to being a blobby shape and then it's there. Yes. Einstein said God does not play dice with the universe. That's why he is quoted. That's what he is quoted as saying. And I don't actually understand what he meant by that. I don't know what he was talking about. But it has to do with like probabilities and stuff. Yeah. So you guys probably know better than I do because you probably watch things about that.
But who cares? Schrödinger had made an important discovery. He had found the shapes of hydrogen. And using that as a basis, those that came after him were able to find the shapes of all the other atoms. They are very much based on hydrogen. They use the same orbitals. It's just that the higher atoms consist of more electrons, therefore they require more orbitals to house all of them. So you end up with a situation where the orbitals all get stacked on top of one another, overlapping but not mixing. They do, however, repel, because that's what the electrons do, they repel one another. So the orbitals begin distorting each other according to some very complicated math. But these guys were also good at what they were doing. And combined with Schrödinger's discovery, they had now made a link between physics and chemistry. A link which in fact led to an entire revolution in both of them.
Okay, so if we look, what do we owe to quantum mechanics? We owe lasers, MRI scanners. I don't know what quantum electron dynamics is, but it sure sounds fancy. Molecular design, rocket fuel, interstellar molecular spectroscopy, transistors, computers, diodes, electron microscopes. None of those things would be possible without quantum mechanics.
So with that, I would like to conclude by just saying, Mr. Schrödinger, thank you very much.
Okay. So, what do you need to know about the Schrödinger model? You need to know the man's name, Schrodinger. You need to know the two names of the model. Tell your partner what the two names are. The electron cloud model and the quantum mechanical model, and you need to be able to draw a proton in the center with the crazy like hyperactive flag kind of thing going around the outside. And that's it. This is just to pique your interest. If you're interested in this sort of thing, you might want to take some physics courses. We do a little bit of this in enriched chemistry as well. Yes. Truly, honestly, we spend a lot of chemistry lying to you about things and then telling you the true story later. Because the true story is more complicated than, say, even I can understand, right? And I'm your teacher, right? Than Einstein feels happy about. Do you know what I mean? So why would we bother you when we have these wonderful models that make useful predictions that allow us to say, oh, this is how things happen, and I can visualize it. So that's why we do that, and we just kind of slowly introduce you to the real nature of stuff. But it's so weird that it's kind of nice to be able to just fall back on some, okay, even though this model is not correct, it's actually visualizable, so we use those a lot. No. Well, no, I'm lying. There's string theory, which I know nothing about. Don't understand string theory at all. Like, I don't know. Yes. Yeah? Yeah. 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 All matter is made of energy vibrating at different frequencies. That's, you know what? It sounds good to me. I'm going to go with that. That sounds good. We're going to take a 5-minute break, so we need to be back at 22. And then Tyler is going to talk to us about isotopes. For gases, they're not brittle, but if you were to freeze them, they would be. That's there's not really the enriched version. So, hi. Can you redo your? Yeah, yeah. Is there anyone who needs to do or needs to redo the atom model quiz? Is there anyone who needs to do or redo their atom model quiz? I haven't given them back yet. Why don't I get those for you? Okay, models of the atom.
Can I see what I got first and then?
I haven't marked it yet.
Oh, okay.
So this is for people who know they bombed it.
I failed it. So if I.
So don't worry, you can redo it later if once I've marked it.
Okay,
if you find you're not here for that. Okay. There you go. Yes, quiz. You see, so I would like it'll look like this, but the boxes will be empty. So this box that says alkali metals will just be blank and you'll have to write alkali metals.
So we don't actually have to write like the elements.
Oh God, no, no, no,
Okay.
no, no, no. You're like, oh my God, it's all blank and I need to fill in it. No, 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 no. So it'll be like, this will be like, I won't have you write other nonmetals, but halogens, noble gases, alkali metals, vein
We'll have to write
groups.
metallurgy, right?
Yeah.
All right, well, so we'll just get a giant chart of this and write main group elements and stuff?
Or I might say what groups are the main group elements.
Okay.
Yeah. I,
So,
okay.
So I'm gonna need like the practice.
You'll need the practice quiz today. Very good. Very good. Very good. So here's the practice quiz. Okay. It pretty much looks exactly like the regular quiz. The only thing is that
Thanks to Google for sponsoring a portion of
No.
this video for supporting small business.
Shush. The only thing that is missing if you do the enriched quiz is that this will be blank, so you can just put a piece of paper over it if you want to do the enriched thing. Yes? Yes. Okay, let's grab that for you.
I guess we'll just do my test on Tuesday.
Yeah, that sounds good. Yep. Hi. You want to do that? Yeah. There you go.
Thank you.
Would I be able to get a test?
Sure thing. Okay, sure. I love it. Yes. Tyler's going to teach us a little something about isotopes just before we head home today. We are on page 84, 84. Page 84. What's that? Oh, well, you see, we have like a progression, right? We go from Bill Nye, who is like the obsession of a couple people in my other class. Are we watching Bill Nye? I'm like, no. And then we have Tyler, who explains things in a really nice and gentle way. And then we have that other guy who explains it quite quickly, who talks very quickly, but it's kind of fun. He's much more tolerable now. Like I don't like the little kids show because I find it's like overstimulating for me. There's like yelling and moving and but yeah. Okay, here we go. Let's go watch about these isotopes. Isotopes.
What are isotopes?
Page 84, 84. And this video is not as loud as the other ones, so you might have to be a little quiet, okay? To be able to hear.
Isotope is a word that gets thrown around in chemistry a lot. So, like, what are they? Really quickly, isotopes are different versions of an element, or different versions of a certain kind of matter. This can be a tricky concept, though. A lot of
Okay, so your first blank is isotopes are different versions. Page 84, 84, versions. We had someone mishear it in the other class. They thought it said virgins, and I was like, no. I'm like, no. That would be the other unit in biology. Okay.
people get confused by isotopes. So I want to describe them by starting out with an analogy to cars, okay? I want to talk to you about the made-up car called the Lamona, the epitome of luxury, and it's known for its very distinctive styling. As you'll see, the Lamona looks like a lemon. Now, the Lamona comes in three different models. There's the Lamona G, the Lamona GX, and the Lamona GXL. They're all different colors, as you can see, but each of these models also has unique features. One has radial leather seats. The GX here has chrome wheels and a CD player, it's blue. The red GXL has massaging seats, platinum spinner wheels, and everything. But here's the point. They are all Lamonas. They're all Lamonas because they all have this distinctive style. They look like a lemon, and that's what makes a car Lamona, okay? So it doesn't matter what color it is, and it doesn't matter the various options that you get in these models, the GX or the GXL. What matters is that they all have this particular shape. That's what makes a Lamona a Lamona. So we have these three different models. I want to use this analogy now to talk about the same thing but with atoms.
So you're going to flip to page 85.
I want to now introduce you to three models of carbon, just the way there are three models of aluminum. Okay? Here are the drawings of each one of them, and what we're particularly concerned about is the nucleus. I'm using these red dots to symbolize protons, and I'm using the blue dots to symbolize neutrons. The swirly circles are supposed to represent electrons that are buzzing around the nucleus, but we don't really want to worry about that too much right now. Anyway, these three models of carbon are carbon 12, carbon 13, and carbon 14.
I would like you to to take a look on page 85 and decide if you can tell why these are called carbon 12, carbon 13, and carbon 14. Once you've figured it out, tell your partner. Okay, so why carbon 12, Jade? Yeah, if you add up all the protons and neutrons, this one has 12. This one has 13 particles in the nucleus, and this one has 14. Now, do you remember how much does a proton weigh? One what? AMU. What does AMU stand for? Atomic mass unit. So this number here tells you the mass of the atom in atomic mass units. So an atom of carbon 13 weighs 13 atomic mass units because it has 13 protons and neutrons altogether. Okay?
Let's look at the options in them. Like we did with aluminum, let's look at how each one of these different types of carbon differs. Okay? So if we count the number of protons in carbon 12, we'll say it has 6 protons. And if I count all the blue spots here, I have 6 neutrons. Okay? Carbon 13, 1, 2, 3, 4, 5, 6. Red spots, 6 protons. In this one, I have 7 neutrons. And in carbon 14 down here, I have 6 protons, and I have 8 neutrons.
You can fill those in. And then I want you to think, what is the same about all atoms of carbon? Once you think you know, tell your partner. What is the same about all the atoms of carbon? Thank you. All the atoms of carbon have 6 protons. Now, let's go just to our periodic table for 1 minute. And let's go look at carbon. What's special about carbon that we see here? It is atomic number 6. So it is the atomic number that tells you the number of protons, and it is the number of protons that defines what element it is. If you have 6 protons, that means it can form graphite, and you can use it in your pencil and will have all the properties of carbon. Now, if you were to somehow stuff another proton into the nucleus, so you had 7 protons instead, would you still have carbon? No, what would you have? Nitrogen. It would have a whole different set of properties. So it is the number of protons that determines what the element is and what its properties are. Okay? But we can change the number of electrons and we can change the number of neutrons. We're just worried about neutrons right now. We'll talk about electrons probably next week, maybe tomorrow. Let's see how we do. Okay, back to the video. Where is it? There it is.
So what do we have in common here? All the different models of the Lamona, even though there are things that they differed about, all have the same distinctive lemon-like shape. So for carbon, what they all have in common is they have 6 protons. 6 protons in the nucleus. And that's what makes a carbon atom a carbon atom. Okay? So it turns out that it doesn't matter how many neutrons it has. 6 neutrons, 7 neutrons, 8 neutrons, no big deal. It's just like painting the Lamona in different colors or adding a radio or a CD player. The neutrons, it doesn't matter. It doesn't change the fact that each one of these are a carbon. That's because carbon is defined it has 6 protons in its nucleus. If you look it up in the periodic table, you'll see something that looks like this. And the number up here is the atomic number, 6, which means that if an atom has 6 protons, it's carbon. Okay? So that's what these all are. They are all isotopes of carbon. They're different versions of carbon or different models of carbon with the same number of protons and different number of neutrons. So look at how I wrote this. I've got carbon 12, carbon 13, carbon 14 up here. I want to take a minute and talk about the numbers. So the number of protons in the nucleus, we call that the atomic number.
You can fill that in. That is
You may
the
already know.
atomic
Carbon 12,
number.
this 12 that I've written here refers to a different number, and we call that the mass number.
Okay, so the 6 is the atomic number. That's the number of protons. The mass number, what is the mass number equal to? Yes? Number of protons and neutrons together.
The mass number, as you'll see, is the number of protons plus the number of neutrons. So this is carbon 12. 6 plus 7 protons and neutrons is 13 here. 6 plus 8 is carbon 14 here. So that's how we distinguish between these different isotopes, different types of carbon. There's another way that we sometimes indicate these different isotopes and atoms instead of doing 12, 13, and 14. And that's by using something called isotope notation. Let me show you how we do that. The way we write carbon 12, 13, or 14 isotope notation is we start out with a chemical symbol. If you don't already know that, you can find it on the periodic table. So here it is. It's a big uppercase C. So I start with my C for carbon. And then on the lower corner here, I write the atomic number. So that's going to be 6. And then up top, I write the mass number, which is 12. So this is carbon 12 written in isotope notation.
Now, sometimes people mix up which number goes where. I'm going to show you how you can remember that the big number goes on the top and the little number goes on the bottom. You can actually use this isotope notation to calculate the number of neutrons. Because if you take 12 and you subtract 6, what do you get? 6. So which way do you normally subtract? Do you normally put the bigger number above and then you put minus 6 equals 6. See if you can draw in the numbers in the next isotope notation, the next one down for carbon 13. See if you can draw those in. And then Tyler will show you.
Carbon 13 is going to be 6 again, because all carbon has 6 protons in its nucleus. Then the 13 up here.
Okay, so we would go 13 is the mass, minus 6 is the protons, and that leaves us with 7, which is the number of neutrons. Okay, so that isotope notation is fairly handy for figuring out how many neutrons you have. It's very tidy that way.
And finally, carbon 14, written in isotope notation, is C614.
Okay, so we now have 14 minus 6 gives us 8. And we're done for the day. We're just going to leave it there. There's a little bit more in here. We'll take a look at it next day. But your homework is here. What's that? That's AP Chem. This is not you. Sorry. This is you. Pages 75 and 76. Thank you for catching me on that. You didn't want to be doing AP Chemistry. 75, 76.
Excuse me like a stranger.
All right, let me grab those. I just put down, did I put them here? Yes, I did. Hooray. Get through this as quick as we can so you can go home. All right. Oh, that was very cool. Very nice. Yeah. Okay, I'll tell you my class for the final is like okay. And don't like the course does go like till the end, so don't leave too early. Okay? Like it's full. We are full. Okay? Yeah, so that one was good. And this one, that's good. Yeah, yeah. All right. So where did we get to? Here. So we're going to use the trend line. The 4 hours. Okay. Now, do you know what kind of bar graphs are useful? Yeah. Yeah, exactly. So you want different groups. Okay. So when you find something in here, let's see, how much oxygen dissolves at different temperatures. That's how much groups. Now, what's the effect of molecular mass on boiling point? That's how much groups. Average height, height. Are you here to do corrections? Yeah. Okay, come on, come sit up here beside me. That sounds good.
not injected get injected also got sick. When these chickens got sick, those chickens got sick. So was the idea that the bacteria caused the disease? Was that correct or was it wrong? Because yeah, no matter if they got the bacteria or not, they all got sick. Okay? All right. And then Dr. Eichmann, Dr. Eichmann noticed that all the chickens before the experiment, they all ate whole grain rice, brown rice. Okay? During the experiment, though, they were fed polished rice. So that's what the white rice. Okay? So everybody got whole grain rice before, but during the experiment, they all got white rice. And the white rice was missing a vitamin. Okay? It's missing a vitamin. So what do you think? Dr. Eichmann, what do you think we thought in the test? Not the bacteria. What is causing? Yeah, yeah, good, good, yay. All right. This is good, this is good. Oh, this one here, that one. So, do you remember what I told you? No, okay. That's the one that gets no treatment. If there was a group up here that gets no treatment, are you unsure what could it be fine? No, that means we are also sure about rat serum. So what do you have to do? More. When you're sure about it, you have to put more. Yeah. Yeah. Okay, good. Now this one, same thing. Are you sure about that, or could it be us? Sure. So yeah. And beautiful. Okay. Yeah. Yeah. Other than that, you're okay. That's correctly. Good. Okay. Okay, this is good, and this is good, and this one is good. This one is now, that's not why they rejected. They didn't notice that until after the experiment. During the experiment, what happened that the experiment that the bacteria? What do you think about that? Yeah. Yeah, perfect. Fine. Okay. So you, other than the fact that most of it, okay, group over here that was injected with the vector. But there was another group of chickens that was not injected. Because this group got the shots, this group did not get it. Now, who got sick? The active chickens became sick. But so did the uninjected. These guys got the bacteria and they got sick. These guys did not get the bacteria and they got sick. So what are the bacteria that cause yeah. All right. Now, Dr. Eichmann, he noticed something. This is after the experiment. We're like, oh, it wasn't the bacteria, it wasn't the yeast. Thinking getting good. He's like, what could it be? So he said he did some reading and did some looking at what happened. Before the experiment, all these healthy chickens, they were eating whole grain rice. But during the experiment, they fed the chickens polishers, white rice. And he's like, oh, that's interesting. And he found out that the white rice was missing this vitamin called iron. That's very interesting. So what he thought, yeah, yeah. It's really hard to control the number of bacteria in the toilet. So what is that? The plan is what you're actually there's a group wise, the highlighting of mouthwash, the 50-second. What should be the thing about me and the mouthwash? Not the brand of the mouthwash, but what about the mouthwash? Yeah. Yeah. Absolutely. It could be like, you know, you push it through your teeth or you know what I mean? Like there's different ways to instructions. How to apply. It all is the same. You could say, other examples. Okay, this is another one. That's correct. Okay. Some other examples like you do not have a mouthwash. Like you know, well enough and what the person has other people said, before, right? Yes.